rules. So let n be a positive integer. Do you know what integers are? Whole numbers. But integer includes a negative number as well. So -2 is also called an integer. So positive integer is exactly whole numbers, right? So ddx x to the n is, according to that table, what is the answer to this one? N comes down and x raised to n minus 1. Is that right? Right. So we didn't prove this. I just gave you this is it, and then you memorize it and used it so far, right? But all of us wonder, why is this true? So I'm trying to answer why this is true. Okay? So here, case when n equals 2. How about that? Can we actually prove that? Well, it's case n equals 1. Case n equals 1. ddx x equals the first, right? We're not using that table, the derivative rules I gave you. We're actually explaining why that's true. So how would you explain this one? You can go through the definition. Remember, there's a hard way of calculating a derivative. You went through this, all the h's spreading apart, and you cancel that. If you go through, you can verify this is 1. But if you look at the graph of y equals x, what is it? It's a line, right? Y equals x. So everywhere is a tangent line itself. The slope is always 1. Does that make sense? Right. So since y equals x is a line of what slope? Slope 1. Isn't that it? So everywhere is a slope 1. Make sense? That's why it's 1. Let's do case 2. ddx is x squared. What is that we learned today? Product rule, right? Do you think we can use a product rule? And we proved it, right? So that we can use it as a part of the proof. ddx. How would you write it as product of two things? X times x. Do you think you can apply the product rule? Okay, what is it? First factor differentiated, right? We just did that. First factor is differentiated. First factor is x, so that's 1. Does that make sense? Right. X is not touched. The second one, which is x differentiated and something which is worked out, which is 1 again. So what is it? 2 times x. Right? 2 times x. And the rule says ddx is x squared, and 2 comes down, and x to 2 minus 1. Isn't that what the rule says? And it's supposed to be 2 times x to the first, which is what we have calculated here. Not using that rule, but using the product rule, we proved it. This rule that I gave you wasn't proved. I just proved the case when the exponent is 2. Does that make sense? All right. What's next? Case n equals 3. That's right. Good. So let's try that. ddx x to the third. All right. Can you write down as a product of two things? Sometimes there are several choices. Most thing works. What is that? What is one idea? X times x squared. That'd be all right. Let's do that. Derivative first factor, right? What is it? 1. Second factor untouched. First factor untouched, and derivative of the second factor. Are we using the rule from the table, or are we using something else to differentiate this one? We're using the something that we have established before, right? Right above this line, we prove that x squared, the derivative is 2x. Right? It's not using any law. We just did that work. So we use that in here. 2x. Not pulling out any rules or anything. We just did it. Okay? It's like that. Always you did the work right before so you can use it. So entirety is actually the proof. It's all self-contained. I'm not using anything else except the product rule, and the derivative of x to the first is 1. So how does it simplify? X squared, 2x squared, is that right? What is that called? 3x squared. And then you go back to the rule. The rule says d dx x to the third, and 3 comes down, 3 minus 1, and 3 times x squared. Checks, right? So we prove that case. So mathematicians wonder, is there an efficient way of we don't want to do this forever, then like in an efficient way to write down the proof, right? So here's how mathematicians wrap up this type of thing. So we've been using the previous case to establish next case, right? So this is how they do it. Assume we proved d dx of x to the n is n times x to the n minus 1. Assume we proved that. Not using the rule, whatever, we proved it, self-contained proof. And use this to prove about, to compute, not prove, to compute d dx of next level. What is next level? N plus 1. So if you have one case established n, then using that property you can always establish the next level without using the rule you were about to prove, right? So you can't use that rule from the table. You have to use something else that we have already established. They think this chain proves in entirety. This is called mathematical induction. But you have to work out at least one case so that logic starts from some truth, not fictitious truth here, right? You can't just assume this is true. You have to establish at least the one case. Then rest apart is a chain reaction. Does that make sense? This chain reaction of a logic is called mathematical induction. It requires some checking some previous cases. Does that make sense? Logic makes sense? So let's do that. We're not using that rule, right? Then what else can we do? Product rule. That's all we have right now, right? So let's do that product rule. What do? You split it, just like we did before, x times x to the n. Does that look right? Okay, so the derivative of the first guy is 1. First factor, right? Second factor untouched. First factor untouched. Second factor differentiated. But what rule are we using is a trick question. To differentiate this one and here, what rule are we using? Not the rule. The work that we just did it in the previous stage. Just like that we did it before. So it's not a rule or anything. We just independently proved that statement earlier stage. So we use that work we just did in here. So what is that? N times x to the n minus 1 from earlier case. So we call this a induction hypothesis. We have worked on the earlier stage, so we can use it in the next stage. Isn't that what we did over there? Right? To prove n equals 3 case, we use the work on the n equals 2. Does that make sense? Yeah. So it's a general discussion, description of that. So let's simplify it. X to the n, and here n is out there, and together, what is the power? 1 power and n minus 1 power there. All together is x to the n. So x to the n factor out, right? So you have 1 plus n raised to the x to the n. That's the calculation you get if this one is true. So now you look at the rule. Rule says d dx x to the n plus 1 is that n plus 1 comes down, right? And you subtract 1 from the n plus 1, the exponent. And you simplify it, and then it turns out, according to the rule, they're asserting this is true. But now you're verifying that, hey, that's what we just calculated from the result we just established in an earlier level. And to mathematicians, this actually proves that it holds for all the positive integers. What is this technique called? Mathematical induction. It requires actually calculating, not like this, actually calculating the very first case, then this chain reaction proves all the entirety. It's called mathematical induction. So I actually proved it in a very, very nice way using this principle of product rule. Then this is always true. Didn't factor anything, didn't go through any limit calculation. Leibniz's idea. This logic actually gets you somewhere really quickly in an efficient manner.